students, we have been discussing on ternary phase diagrams. In the last class, I just started on the discussions on the ternary phase diagram. So, the first thing I told you is that in a ternary phase diagram, there are two composition variables which are independent, because there are three components A, B and C. So, there will be the three compositions variables x A, x B and x C, where x A, x B and x B C represent the mole fractions of individual elements. Now, as we know that x A plus x B plus x C is equal to 1. So, therefore, because of this because of this equation, only two composition variables are independent, but the third one is dependent, right. And in a phase diagram, as you see in the binary phase diagrams, there are two variables, one is a temperature, other one is a composition. Pressure is always kept to be constant. So, similarly, in ternary phase diagram also we keep the pressure constant at 1 atmospheric pressure. So, we have a temperature as one of the variables and composition as the two variables, right. So, therefore, the phase diagram will be a 3-dimensional structure, a 3-dimensional plot. Now, how we generate that thing? So, I start with the composition. Composition is represented by using a triangle known as a Gibbs triangle. Gibbs was a well known, a very profound scientist who has given many relationships in thermodynamics. To honor that, this triangle is named after him. So, Gibbs triangle is a equilateral triangle. So, all the three sides of the triangle has equal length, and angle subtended by these two sides is basically 60 degrees. So, now question is this: if that is the case, if you have three sides being the equilateral triangle represents you the compositions, as we have seen there, as you could see here that this is represented here. You have a point A, B and C and three sides A, B, B, C and C M. That is the equilateral triangle. So, how do you represent the compositions? The corners of each of these corners of the triangle represents 100% of the pure component A, B or C, correct. That is the point 1. So, corners represents 100% of component, any component. Now, come the sides. So, you have three sides A, B, B, C and C A. Three sides A, B, B, C and C A. So, each of the sides represents one binary, because as you know there are three components A, B, C. So, there will be three different types of binaries A, B, A, C and B, C. So, each of the sides will represent binary composition. So, if I follow on AC line or AC side, so AC sides will represent compositions of A and C only, there will be no B, B will be 0. Now, similarly AB will also be, similarly BC will also be. So, there are three different sides of different side AB, AC and BC. Now, each of these sides will represent, as I told, each binary component. That is correct, right. Now, so if that is the case, then whatever the point inside the triangle, points inside the triangle will represent ternary composition. Ternary composition means each point inside the triangle will tell me composition corresponding to A, B and C. So, any alloy having containing A, B and C has to be represented by the point inside the triangle. These are the three very important aspects you must remember. So, that is how we actually generate or we can plot the compositions on this Gibbs triangle, correct. So, I told you also that there are very distinct ways of dividing this triangle, and what are the ways? First is that you can divide the triangle using these lines which are parallel to either BC, AB or AC. Okay. So, any line parallel to BC will represent compositions of A, right. These are the lines particle you see 1, 2, 3, the 10 lines, each one representing 10%, 10, 20, 30, 40, 50 up to 100%. So, that you can reach 100% A at the corner. So, any line parallel to AC will tell you the compositions of B, any line parallel to CA will tell you the composition of B. So, that is how. Now, if I want to know the composition of any point, what I do? Suppose this is the point I want to know compositions, okay, or let us say not do that, let us do that this one. So, what I do? I draw a parallel line with respect to the AC. So, this will tell me the B compositions. How do you know? B is like this is 10% B, 20% B, 30% B. So, this is 35% of B, very easily I can get. So, it contains 35% of B, weight percent of B. Now, how do you know what is the composition of A? I draw a parallel line with respect to BC, correct. So, this will tell me A is like 10%, 20%, 25%, 25% is A. So, obviously, if I know A and B, C is automatic, 35 plus 25 is 60. So, 40% will be C. That also you can measure, C will be coming from parallel to this. So, you can see here this is 10%, 20%, 30%, 40%, this point is lying on 40% of C. So, that is the easiest way of measuring compositions. Let me erase these things because we will use. Okay. Now, as I told you, these sides that is BC will tell you the composition of B and C. So, that is very simple in binaries also. Suppose this point contains 45% of C and 55% of B. That is how we can do. There is another way of representing composition. That is it what I told you here. Suppose if I want to know the compositions of point P, or if I want to present some compositions which is known, that also can be done. So, what I do is that I draw a vertical lines 1, 2 and 3 vertical lines, okay. Here the vertical lines correspond to PP1, PP2, PP3, okay. There are 3 vertical lines. This is what I discussed in the last class also. So, now PP1 opposite to A, this is opposite to A, this will tell me the percentage of A, this will actually tell me the exact percentage of A. We will come to know how to ratios we can easily obtain, how to get the composition will tell you later. So, if I take ratio of PP1 versus PP2 plus PP3, so they will tell me ratios of A is to B is to C. Now, to know the compositions, what I do? Okay, here, let us go there. To know the composition, suppose this is the point X. So, I draw normal to AC, normal to BC, normal to AB, okay. The 3 normals, and each of these 3 normals are sitting on these curves, correct. Now, question is this, to know the compositions of A, I take the normal which is sitting opposite to the point A. So, here you see XM is just a normal sitting opposite to A. So, A concentration is basically XM divided by the AM or MA, MA is the whole thing, just like a lever rule, okay, opposite arm. Similarly, if I know the composition of B, I go to the opposite thing of B, that is XM divided by BN. Similarly, if I know the compositions of C, I took the length XL divided by LC. That is what is done. So, there are 3 ways of measuring compositions, I told you, and you can use any of these to present composition. Suppose some alloy contains 50% A, 20% B and 30% C. So, you can actually use any of these 3 techniques to put the compositions on this chart, correct. Now, what I am going to do is this next 10-15 minutes before is that I am going to talk about the tie lines and the triangles in ternary phase diagram, because these are very important. I hope you remember what is a tie line in a binary phase diagram. Let us start with that, okay. Let us start with a binary tie line. I draw a binary isomorphous phase diagram like this, temperature versus Xp, pure A, pure B, okay. So, now what it will do? I draw a tie line, this is a tie line. What a tie line does? It connects the solidus with the liquidus. This is solidus, this is the liquidus, okay. It connects that solidus with the liquidus. So, what does it tell you? It tells me that liquid composition and solid composition. So, I can draw many tie lines, and I can find out. So, in fact, whenever you talk about composition, solidification of the alloy, suppose I have to talk about solidification of this alloy, I just follow the tie lines to know the composition of solid and liquid phase. Same thing can be extended in ternary. Okay, let us suppose I have an alloy with a composition given by point x. Okay, here I am showing only one corner of the Gibbs triangle. You see here, this is point C, this is point A, this is point point B will be there, point A will be there. Okay, I am just showing you the one corner, so that you can realize it nicely. Now, if you look at this x, okay, x, right, x is this. X in alloy x is separating into two alloys, two phases, alpha and beta. So, alpha composition is given by this point, beta composition is given by this point, correct. Now, how do I apply the, how do you find out what is the volume fraction of alpha, how is the volume fraction of beta? That is what we do using tie lines, right. How do you do in binary? Very simple. Suppose I am just showing it for this, let me just erase this, then only it is easy to show you. Okay, otherwise you will get confused. So, suppose I have alloy composition x, and it is and I am at a temperature T1. So, therefore, there is a solid, there is a liquid, there is a solid, and this is my solid compositions, this liquid composition, this is my solid composition. So, I write down this is xs, this is xl. So, this is my line, this is x, this is xl, this is xs, sorry, this is xs, because this is the liquid solid as xs, xl. So, now if I want to know liquid and if I want to know solid, what do I do? If I want to know solid, I tell xlx divided by xs xl, right, into 100. So, this is my solid percentage. Liquid percentage is what? Liquid percentage is opposite term, x xs divided by xl xs into 100. That is what I do. Same thing I can do it here also, but before that we have to know the compositions. Let us suppose, and we do not need all A, B, C, we can use one of these. Suppose if I simply want to use B compositions. So, what I do? I do parallel lines, parallel lines with respect to the CA. So, I do a parallel line like this, one parallel line passing to point beta, another parallel line passing to point x, and third parallel line passing to point alpha. So, these parallel lines if I extend, they will hit these CB curve or CB sides at these points. So, they will tell me the compositions of B in beta phase, and tell me compositions of B in alpha phase and composition of B in the overall alloy. So, now I can do the same thing. I can use this line 1, 2, 3 points. I can use this same line with these different points. I can use that same lines with these different points. Okay, 1, 2, 3, same lines, and use the same mathematics which I did just now for binaries. That is the analogy. Analogy is very clear. One can actually use same analogy. Only thing you are doing extra job which you do not need to do in binaries is that you have to draw these parallel lines to measure compositions. But remember, you have to know only compositions of one of the PCs, either A or B or C. You do not need to do for everything. Similarly, suppose somebody may say, I will not draw parallel lines with respect to AC, I will draw parallel with respect to BC. So, if I draw that parallel line with respect to BC, I will an extent that will hit this AC line or AC side at XA alpha, XB beta and XA, these 3 points, correct. Now, using again this as a tie line, because this is the extension of the tie line, what we are doing is projecting, right, finally speaking, mathematically we are projecting this inside line onto the sides, each of the sides, and getting to know the compositions. And again using this composition, we can use the mathematical rule of lever rule, apply that and get volume fraction of the phases. Very clear, right. So, you can have a situations where one alloy with a fixed compositions separated into 2 phases, then this is very nicely done. But in ternary system, this is very low probability situation. In ternary alloys, you will most of the cases will have more than 2 phases. In that case, you cannot apply tie line concept. What you should do is you should apply what is known as tie triangle concept. To give an example, suppose you have an alloy composition given by X, correct. This alloy is separating into 3 phases alpha, beta and gamma, and you want to know what is the volume fraction of alpha, beta and gamma, right. That is what your task is. Suppose, as I told you in the last case, what did I tell you? I tell you that if an alloy the composition X separating into 2 phases alpha and beta, and the compositions are lying inside the triangle, then I can measure the volume fraction of these phases alpha and beta using the lever rule, same lever rule what we have used, but I have to do some constructions, and those constructions is very simple. I told you. Now, as I told you that an alloy separating 2 phases is a very low probability one. Most of the cases alloy will separate into more than 2 phases. This is a situation where an alloy separated into 3 phases. A alloy composition X is separated into alpha, beta, gamma, and you have been asked to measure the volume fraction of these phases at a particular temperature. How will you do it? Well, very not difficult. First thing what I will do? First thing I will do is that this is called a Gibbs, this is a triangle, that is why it is called a tie triangle. First thing I do is that this point gamma is I connect to X and I extend up to Y, okay, correct. Now listen carefully. So now this is my line, tie line, correct. So I can measure the compositions of this point and this point by drawing parallel line with respect to BC. So I draw a parallel line here, one, here another one, here another one, correct. So this is my gamma, this is my X, let us write gamma prime X prime and Y prime. So I can apply the lever rule here and measure the volume fraction of gamma and also volume fraction of suppose a fictitious phase Y. I can do that because that is a tie line. Now, so therefore, this Y then I can assume. So first job is that you extend this line to alpha beta, so that it hits the point Y, correct, hits the point Y. If it hits the point Y, then I can measure the volume fraction of the phase gamma and volume fraction of the phase Y. Now question is this, so that means what I have done? I have done that this alloy X has been separated into 2 phases gamma and Y, but that is my assumption. Now Y is again separated into 2 phases alpha and beta. So now I can simply do this maths. I suppose I have 60% Y and 40% gamma. I can use this as a tri line, okay, alpha composition, Y composition and beta composition, and then whatever percentage of alpha I get, I multiply that with 60%. That is how I can calculate alpha, beta and gamma. So you understand. So if you have 3 phases or 2 phases, very easy. Once you have 4 phases, things will be very, very complex. Actually, you can use 2 tie triangles to do that, but let us not discuss, because I do not want you to getting confused into that. Let us think about 3 phases, because as I know in a ternary system, maximum number of phases present will be 4, not more than that, okay. F is equal to 0 corresponding to 4 not phases. So what is the reaction which is possible? Suppose a eutectic reaction in a ternary system, liquid going to alpha plus beta plus gamma. So alloy of X composition, liquid will vanish and form 3 solid phases. So basically you are measuring volume fraction of 3 solid phases, you do not need to measure volume fraction of liquid present. If it is required, I will tell you how to do that. It requires a detailed discussion, but it is possible. So what did I tell you in a very light way, because these are things as I go along you will forget, that is what I have to tell you again and again. First thing I am telling you only the composition aspect, how to measure compositions, how to plot compositions on the Gibbs triangle. So whenever you are listening to these lectures, please try to take a print of Gibbs triangle from internet site or even books, Xerox copy of that. Then look at it when you are listening this lecture and try to contemplate that you are listening the lecture, also you are doing the maths or plotting it simultaneously. Then that will help you, because in ternary phase diagrams people get scared quite a bit, but this is not difficult, this is easy. One has to understand the basic things very well, then you can do it. So, this is what is important. We will discuss what are the issues of ternary triangles for these things in the next class, but let me just, before I end this class, before I will just like to tell you that now I have given you Gibbs triangle, told you, not given you, I have told you Gibbs triangle plot compositions. Now I can just put a vertical axis temperature axis, okay, vertically like this on these things. So, once you put a vertical axis, this is a temperature. So, you have three composition XA, XB, XC and vertical axis temperature. Now, we can plot the phase diagram inside of it, correct. So, just to show you that suppose there are three components A, B, C and three of them are forming isomorphous phase diagram binaries, BA form isomorphous, AC form isomorphous, BC form isomorphous. How the phase diagram will look like? Phase diagram will look like this, a 3-dimensional lens separate thing. You can clearly see, I do not know whether you can visualize it, a 3-dimensional lens separate. Basically, it is like a conch shell like this, conch shell like that, okay. Can you see that? Conch shell like this. So, therefore, the phase diagram is also very simple. So, now our basic purpose will be to understand what is there inside, and this is very simple case, that is why you can see it and we can understand it very easily, but there will be complex diagrams inside it. So, for those we cannot simply see the 3-dimensional picture and understand. What you need is 2-dimensional sections, because we are very comfortable with 2-dimensional sections. Human beings are very comfortable with 2-dimensional pictures, although we ourselves are 3-dimensional, but we are very comfortable with 2-dimensional pictures. We are very comfortable. Anybody even not from mathematics background, they can, or physics background or science background, can understand 2-dimensional picture. The moment you start talking 3D pictures, they have to meditate and think, that becomes difficult. So, that is why for very complex things we will take sections across these diagrams. Sections can be horizontal sections at a fixed temperature, because vertical axis is temperature. So, horizontal section fixed temperature, or you can take a vertical section also. So, few things which I have to teach in the next class is, first I have to tell you what are the rules and regulations of the tie lines, whether they are same or not. Second is vertical horizontal sections. Please remember, these are all there nicely in the books of Alan Prince, but I will try to explain and move slowly so that you can understand things very easily. So, with this I just finish this part of lecture, and next lecture we will take up other issues. Thank you.